Okay, so we're going to continue exploring the different properties of power functions with even and odd degree. So the LC in this little chart that I made, that stands for leading coefficient, and leading coefficient, it's basically it's positive or it's negative, and it cannot equal 0. So a quadratic, so that would just be y equals x squared. It just means whatever is in front of the x. So you can't always see it, so like if there's nothing there, then it's just a 1. And if it's negative x, then it would just be negative 1. So if it was 2, then the leading coefficient would be positive 2. But we're just focusing on the sign, whether or not it's positive or negative or not, because really a number would just stretch it or compress it. But we're just going for the general shape of it right now. So an even degree, so something to the power of 2, 4, 6, 8, etc., that has a positive leading coefficient, that would have the general shape of something similar to a parabola, like a U, and it would keep extending on both sides. So we know that if we have y equals negative x squared, so something that has a negative leading coefficient, then it's just flipped over the x-axis, so it would look like an upside down U. It looks like the exact same thing, just flipped upside down. So now let's look at the odd degree functions. And odd degree, that's important because an odd and an even function are different than a degree of the function. So positive leading coefficient for an odd degree function, it would have the general shape of something like that, as we already explored in the last video. And then if it was negative, the same thing. If it was flipped completely upside down across the x-axis, it would just look like the opposite. So that's what the general shapes look like. Now, symmetry. There's two types of symmetry that we talk about in advanced functions, and there we go. Oh, yeah, there we go. So the two different types of symmetry are called line symmetry. Line symmetry. And then the other type we look at is called point symmetry. And there's ways of figuring it out algebraically, except that's a bit too advanced for this video right now when we're just being introduced to it. But I'll show you how to like graphically tell whether or not it's line or point, because that's in fact much easier to do. So line symmetry means that it has symmetry about the y-axis. So it basically means that if we have a Cartesian plane like this being our x-axis, this being our y-axis, and then we had, let's do a parabola, because a parabola is very basic and it's easy to tell the difference. So this is our parabola. If it has symmetry about the y-axis, it means that if we draw a line down the y-axis, would we be able to completely flip it on about that y-axis, and then would it land and be completely identical to the other side? If it does, if yes, then that function does have line symmetry. So point symmetry is symmetry about the origin, not the y-axis. So, and this also, we rotate it 90 degrees, and I'll explain that just in a second once I draw out a little diagram. So this is our x-axis, this is our y-axis of the Cartesian plane. So we're going to draw not a parabola because it doesn't have point symmetry, it has line symmetry. But why don't we draw a cubic function? A cubic function looks sort of like that. And we know that if we folded it across the y-axis, it would not work. It would just, you know, it would look something like that. It wouldn't line up at all. So it does not have line symmetry, and that's pretty obvious. But what if we rotated it 90 degrees about the origin right here? Let me put that in a different color. And a lot of focus and emphasis on about the origin, because if it's not about the origin, then it's not point symmetry. And that's very important. So,,, 'those both have line and point symmetry. Now, if we had a different function that looked like this, a parabola, but let's say it was shifted to the left by 2 and looked like this, would something like this have line symmetry? And the answer is no, because if you draw a line across the y-axis, then and you flipped it over, it would not it wouldn't be symmetrical. It would look something like that, and that's just, it doesn't line up with what we want it to line up with. So no, this one does not. So not all have line symmetry, only some of them have line symmetry. And you know, we can say the exact same thing about functions with point symmetry. So if let's do the exact same example. Let's say it was moved to the left by 2, and it looked something like this. Since it's about the origin, if we moved it 90 degrees, then it would look like this, and this does not line up with this one right here. Like, there's a distance between them. So no, it is not all functions that generally have point symmetry. Not all of them do. So now let's go back to our other page, the diagram, and let's continue filling this in. They will have generally line symmetry, and that goes for the negative ones as well, and then the odd degree ones will generally have point symmetry, but again, not all of them. So now the end behavior of these functions, what does this mean? Like, I mean, I remember that's what I thought when I was first learning about this. Like, I have no idea what that means. So let me actually create a new layer. All that we do to classify something as their end behavior, we know that the Cartesian plane has 4 quadrants. So that's 1, 2, 3, and 4. And it's basically, where does it start, where does it end? So for a parabola, for example, that would start here in 2, and it ends here in quadrant 1. But what if we flipped it upside down? Then it would be different. It would be 3 to 4. And then same goes for the cubic ones. So this would be, you know, quadrant 3 to quadrant 1. And then if we flipped it upside down, then it would be from quadrant 2 to quadrant 4. So to continue filling in that, the end behavior this is weird. There we go. So the end behavior of the even degree functions, which is positive, would be from quadrant 2 to quadrant 1, which is quadrant 2 to quadrant 1, and then the opposite ones would be from 3 to quadrant 4, and then the odd degree ones that are positive would start in quadrant 3 and then end in quadrant 1, quadrant 3 to quadrant 1. And then odd degree functions with a negative leading coefficient. So I'm just going to draw that up there. That would be from quadrant 2 to quadrant 4. Quadrant 2 to quadrant 4. And no matter what transformations that these functions undergo, it's always, the end behavior will always be the same. So if you can figure out the degree of the function and whether or not the leading coefficient is positive or negative, then you'll be able to draw at least a rough graph of what it should look like. So now the domain and range, I decided that I'd only do the range because the domain for these would all be the same, as the x's, or x has to be all real numbers, and if you continue drawing these out, then x will be all real numbers for every single one of these. So it would be x as an element of all real numbers. So now for the range though, we'll do the quadratic. Let me choose a different color actually. Go pink. We know that the range is relative to the y-axis, and this will vary for whatever transformations you have, but just for a basic one that passes through the origin of all of these, we know that the range would be an element or y must be an element of all real numbers, and then y must be equal to or greater than 0, because it's the lowest point that can be is 0 if it's positive. And then the same thing for a negative. Y is an element of all real numbers, but y must be greater, or sorry, y must be equal to or less than 0, because upside down the greatest point that it will be would be 0 if it has no transformations. And element of all real numbers, it sounds really weird, but it basically means that y could only be real. Like, it has to be an actual number on a Cartesian plane. It can't be an imaginary number, for example, like I, which is root -1. It has to be something real that we can graph. So then odd degree functions, and the video's getting really long right now, so I'm going to go speed through this, would be y is an element of all real numbers. And this continues on and on and on the y-axis. There's nothing that you can do that will change an odd degree function that will not allow it to continue extending to positive and negative infinity of the y-axis. So those are the general properties of the power functions, and we're going to go into a bit more detail about the symmetry in a later video.